So hello students, in the previous class we have gone through different coordinate systems in finite element method. So generally there are three coordinate systems in finite element method, which are nothing but global coordinate, local coordinate system, and natural coordinate system. We have seen what are these. Then we went through even what is the relationship between global coordinate system and local coordinate system. Later on we did a shape function derivation for 1D simplex element in terms of global coordinate. So we'll do a problem on one dimensional simplex element first, then we'll derive what is the shape functions for two dimensional simplex elements, or even you can call it as a triangular element. So problem on simplex element, one dimensional simplex element. The problem is like this: the nodal temperatures of nodes I and J. So while deriving, we called it as node 1 and node 2. So in general, we call it as node I and J. Okay. The nodal temperatures of nodes I and J of an element in a 1D fin are known to be T of I equal to 120 degrees centigrade and T of J equal to 80 degrees centigrade. So while deriving, we used the displacement U. So here, instead of displacement, our field variable is temperature. So temperature is being given to you at node I, that is node 1, and what is the temperature at node 2, that is node J. So with x coordinates, that is distance x1 is given, that is x of I, and x2 is given, that is x of J, which is 30 centimeter and 50 centimeter. So find the following. You are supposed to find out what are the shape functions associated with nodal values T of I and T of J. Okay, you have to find out what is the value of n1 and n2. So once you find out value of n1 and n2, you have to substitute those value of n1 and n2 in the interpolation function, okay, which we have derived. So then once we got this interpolation function, we have to substitute x equal to 45 degree and find what is the temperature at x equal to 45 degrees. Okay, so this is the solution for the given problem. So first we have to find out what is the length of the element, which is given by xj minus xi, so x2 minus x1, okay, so which is 20 centimeters. So in general, the shape functions, first we'll find out what are the shape functions for the given problem. So n1 is xj minus x divided by length of the element. Substitute the values of xj and length of the element. So you will get n1 as 2.5 minus 0.05x and n2 as 0.05x minus 1.5. So you have to substitute these values in this interpolation model. So while deriving the shape functions for 1D simplex element, we got the final equation as u of x equal to n1 u1 plus n2 u2. So here the field variable is temperature, so we write T of x equal to n1 Ti equal plus n2 T of j. Okay, substitute this value of n1 and n2, simplify this, you will get this equation. Okay, this is your interpolation function for the given problem. Okay, T of x equal to 180 minus 2 times of x degree centigrade. Now using this equation, you can find out what is the temperature at any distance. So what is asked in the question here? You have to find out what is the temperature in the element at a distance x equal to 45 centimeter. So if you substitute x equal to 45 centimeter, you will get T of 45 equal to 90 degree centigrade. Okay. So this is the problem on one dimensional simplex element. Okay. So now next we'll move on to deriving the shape functions for 2D simplex element, that is for triangular element. So even in the exam it might be asked like this: derive the shape functions for 2D simplex element in terms of global coordinates, or derive the shape functions for a triangular element. They'll not mention whether it is 2D or 1D or 3D. They might mention that it is derive the shape functions for triangular element in terms of global coordinates. You have to derive the same derivation. Okay, so this is the triangular element which is shown to you, having nodes 1, 2 and 3. Okay, with respect to this global coordinate x and y, the coordinates are written x1 y1, x2 y2, x3 y3, and the displacements at each node are u1 v1, u2 v2, u3 v3. Okay, at each node there are 2 degrees of freedom. So assuming there are two 2 degrees of freedom each node. If there are 2 degrees of freedom each node, you'll be having displacement in x direction and you'll be having displacement in y direction. So u1, u2 and u3 are the displacements in x direction, and v1, v2, v3 are the displacement in y direction. So as you assume the polynomial function for 1D case, here also you have to assume the polynomial function for 2D case, both individually separately for displacement in u and displacement in y direction. So this is the equation which is given here. So u equal to a naught plus a1x plus a2y, and with respect to v, that is with respect to displacement in y direction, a3 plus 4 a4x plus a5y. So these two equations are written separately in matrix form here. So that is u equal to 1xy a naught a1 a2. You can see here 1 coefficient of a naught, coefficient of a1, coefficient of a2. So here row into column, if you multiply back this, so a naught plus a1x plus a2y, you will get back this equation, equation 1. So similarly, it is written with respect to v, that is 1xy a3 a4 and a5. Now we'll see what are the boundary conditions, as we have done it for 1D simplex element. In order to find out the global coordinates, generalized coordinates, that is a0 and a1 for 1D simplex element. Same way, in order to find out the generalized coordinates a0, a1, a2, a3, a4 and a5, we have to use the boundary conditions. So these are the boundary conditions at node 1. So at x equal to x1, y will be equal to y1. You can see x equal to x1, y equal to y1 here. So if x equal to x1, y equal to y1, u will be equal to u1 and v will be equal to v1. So at node 2, x equal to x2, y equal to y2, u equal to u2 and v equal to v2. Similarly at node 3, x will be equal to x3, y will be equal to y3, u will be equal to u3 and v will be equal to v3. Now when you apply these boundary conditions, substitute the equations back in the above equation, okay, you will get these equations. So with respect to u and with respect to v, so u1 is equal to a0 plus a1 x1 plus a2 y1. Okay, see here a0 a1 a2 is common. So with respect to node 1 x1 y1, with respect to node 2 x2 y2, with respect to node 3 x3 y3. Okay, so same with respect to displacement in y direction, that is v1 v2 v3. So you can see here a3 a4 and a5 are same, only with respect to node this is x1 and this is y1, x2 y2, x3 y3. You have to write this equation. Now in order to find out the shape functions for 2D simplex element or triangular element in terms of global coordinates, either we'll use these three or we have to use this three. Okay, so if you use this 3 or this 3, you will get the same shape functions. So either one of these two will be using. So let us use this u1, u2 and u3. We'll write this u1, u2, u3 in matrix form. Okay. So when you write that equation in matrix form, this is what you get. When you write these three equations in matrix form, this is what you get: u1, u2, u3, 1 x1, y1, 1 x2, y2, 1 x3, y3, a0, a1, a2. You can see here the same equation is written in matrix form here. If you multiply row into column, you will get back this equation. You can see a0, okay, x1 into a1, okay, then plus a2 into y1. So you are getting this equation. Similarly, second and third equation, this equation and this equation. Now we have to find out what are this a0, a1 and a2. What are your generalized coordinates a0, a1 and a2? So you have, I'll take this on the other side. Okay, it will become inverse 1 upon this. So it will be inverse of this matrix. Okay, so a0, a1, a2 and inverse of this matrix into your displacements. So you have to find out the inverse of this matrix. So what is the inverse of matrix? Inverse of matrix is nothing but adjoint of a matrix divided by determinant of the matrix. Is it? But in order to find out adjoint of a matrix, you have to first find out what are the cofactors. So once you find out the cofactor matrix, the transpose of that will be your adjoint of matrix. So first we are finding the cofactors. Now you have to find out 9 cofactors. Okay. So cofactor of this first term eliminate this column and this row. This is what is remaining. You have to find out what is the determinant of this. Okay, so you can see here x2 minus x2 y3 minus x3 y2, x2 y3 minus x3 y2. Okay, next, with respect to this, okay, cofactor of x1, eliminate second column and first row, remaining is 1 y2 1 y3, so y3 minus y2, so you can see here y3 minus y2. Now as per the matrix, this is plus minus plus minus plus minus plus minus plus, so minus is their sign, so if you take minus inside, you'll get minus y3 plus y2. Similarly with respect to this, so x3 minus x2, you can see here, let me write those terms here. So this is plus minus plus, so this is minus plus minus, so this is plus minus and this is plus here. Okay, now in order to find out the cofactor of this is how will you get plus here? This is the concept here, minus 1 raised to I plus j. Okay, so this is your a11 or k11, whatever. Okay, a12 or a or k12, so this is a13 matrix. Okay, let me erase this. Okay, so it is like this. Let me write once again, plus, okay, let me erase it. So this is plus, this is minus, so this is plus. Okay, so it is like this. You have a matrix. Okay, so if you have a matrix a11, a12, so a21 and a22, how this plus minus plus comes is because of this minus 1 raised to I plus j. This is I value and this is j value, so minus 1 raised to I plus j, that is 1 plus 1. Okay, that is minus 1 square, so you are getting plus. So here 1 plus 2, so minus 1 cube, so you will get minus 1. Then this is here, this is a13. Okay, 1 plus 3, so again 1 raised minus 1 raised to 4, even number. Okay, this will be even. If this is even, you will get plus. If this is odd, you will get minus. So in that fashion, you will get this plus minus plus minus plus minus, so on. Okay, now let me erase it and let us find out the cofactors for the given matrix. So these are the cofactors. So this we have done it already. So this is the cofactor of this. So this is the cofactor of this, and this is the cofactor of this term. Now we'll find out what is the cofactor of this term. So x1 y3 minus x3 y1. So since minus is there here, so if I take minus inside, you will get minus x1 y3 plus y1 x3. Okay, let me erase. Okay, let me erase this. Let me erase this as well. Now we'll find out what is the cofactor of this x2. Eliminate this and this. Okay, you are remaining with this terms, y3 minus y1. See here, y3 minus y1. Now cofactor of this y2, eliminate this and this, you will get x3 minus x1. x3 minus x1, since minus is there here, so if I take minus inside, you will get minus x3 plus x1. Same, let me again erase. With respect to the last row of the matrix, so cofactor of this term, so eliminate this and this, you will get x1 y2 minus x2 y1. Okay, x1 y2 minus x2 y1. Now cofactor of this, eliminate this and this one. Okay, let me erase this. So you are remaining with y1 minus y2, determinant of 1 1 y1 y2. So you will get y1 minus y2. Since minus is there here, if I take minus inside, minus y2 plus y1. And lastly, cofactor of this. So this is remaining. So determinant of this x2 minus x1. That's how it is. And transpose of that. Whatever we have written, this is your cofactor matrix. Okay, when you transpose this matrix, you will get an adjoint of a matrix. Okay, now let me erase this. In order to make the calculation simple, okay, so we have written this term as alpha 1, this term as alpha 2, this term as, sorry, this term as beta 1, this term as gamma 1. So alpha 1, alpha 2, alpha 3, beta 1, beta 2, beta 3, gamma 1, gamma 2, gamma 3. Okay, so adjoint of matrix divided by determinant of matrix. Why this is 2 times of AE? So half and determinant of matrix, that is determinant of this matrix, 1 x1 y1 1 x2 y2 1 x3 y3 is nothing but the area of this triangular element. Okay, so determinant of a matrix, so this is your area of a triangle. So in the denominator, when you are finding inverse of matrix, it is adjoint of matrix divided by determinant of matrix. So what is determinant of matrix? Determinant of matrix is nothing but 2 times of AE. Okay, now in order to make the calculation simple, we have done it like this. We have written this as alpha 1, this is alpha 2, this as alpha 3, beta 1, beta 2, beta 3, gamma 1, gamma 2 and gamma 3. Okay, now we have to transpose this matrix. When you transpose this matrix, row will uh, row will become column and column will become row. You can see here alpha 1, alpha 2, alpha 3, beta 1, beta 2, beta 3, gamma 1, gamma 2, gamma 3. Okay, and as I've told you, AE is nothing but the area of a triangle, which is nothing but half of determinant of coefficient of matrix. So AE is nothing but this one. Okay, 1 by 2, 1 x1 y1, 1 x2 y2, 1 x3 y3, determinant of this term, half, and determinant of the given matrix is nothing but your area of a triangle. And these are your alpha 1, alpha 2, alpha 3, beta 1, beta 2, beta 3, gamma 1, gamma 2 and gamma 3 values. Okay, now as we have done in the derivation for 1D simplex element, once we find out the generalized coordinate, that is a0, a1 and a2, you have to substitute this back in the previous equation. You have to substitute this in this equation, u equal to, so this equation 1 x y, so equation number 2. Okay, and here a0, a1 and a2. So when you substitute this a0, a1, a2, that is this one in equation 4, this is what you get, and this is what you get. Okay, this is what you get. Now we have to simplify this. We have to multiply this with this, this with this, this with third column. Okay, we'll do that. Okay, so once you simplify this, multiply this row with this column, you will get, and the common term is 1 upon 2 times of AE. When you multiply this with the first column, you will get alpha 1. So 1, that is alpha 1 plus beta 1 x plus gamma 1 y. Similarly, again, this with respect to second column, you will get alpha 2 plus beta 2 x plus gamma 2 y. So alpha 3 with respect to third, alpha 3 plus beta 3 x plus gamma 3 y, and this is as it is. Now as you have done written in for 1D case, whatever the coefficients of u1 u and u2 were your shape functions. Similarly here, when again if you multiply this with this, so coefficient of u1 will be this, and this is the common term for all the cases. So this will be the coefficient. So this is your n1, so this is your n2, and this is your n3, so which are written here. So n1 will be 1 times of 1 divided by 2 times of area of triangle into alpha 1 plus beta 1 x plus gamma 1 y. n2 is 1 upon 2 times of e alpha 2 plus beta 2 x plus gamma 2 y, then n3 equal to 1 upon 2 times of a alpha 3 plus beta 3x plus gamma 3 y, and you know what are the values of alpha 1, alpha 2, alpha 3, beta 2, beta 1, beta 2, beta 3, and gamma 1, gamma 2, and gamma 3. Okay. So this is how you find out the shape functions for 2D triangular element or two-dimensional simplex element in terms of global coordinate. So same thing you will get in terms of when you do it by using polynomial function with respect to y directions. Okay, displacement with respect to y direction, that is v. You will get the same. So when you combine these two, this is what you get. So uv n1 n2 n3, if you multiply back this, you will be getting these equations. Okay, this is equal to like this. U will be equal to n1 u1 plus n2 u2, if you multiply this by this, plus n3 u3. Okay, n3 u3. If you write it in matrix form both combined, this is what is the expression. Yeah, this is what is the expression. Now after this, we will see what is the variation of shape function. Okay, n1, n2, and n3 with respect to the element. Okay. So with respect to the element, what is the variation of shape functions? So these are your nodes 1, 2, and 3, and this is your variation of shape function for node n1, this is for n2, and this is for n3. Now when you apply the boundary conditions, that is when you substitute x equal to x1 and y equal to y1, okay, in all these three equations, okay, all these three equations, you will get n1 equal to 1 and n2 and n3 will be equal to 0. Similarly, when you apply the second case, that is x equal to x2, y equal to y2, so n1 and n3 will be 0, n2 will be equal to 1 as shown here, and these are being joined here and they are shown. This is how the variation of your field variable will be. Okay, variation of field variable. Okay, variation of shape function. And similarly with respect to third one, so here, and you form a triangle here joining, and same. So n1 and n2 will be 0 and n3 will be 1 when you substitute x equal to x3, y equal to y3. This is your variation of shape function for 2D simplex element or 2D triangle element. You have to substitute those values. So you should know what is alpha 1, alpha beta 1, gamma 1, alpha 2, beta 2, gamma 2, alpha 3, beta 3, and gamma 3. Okay, you have to simplify it on your own and check that when x equal to x1, y equal to y1, only n1 should be 1 and rest all should be 0. Okay, you can just check it here once. Okay, so what is n1 here? It contains this three terms. You put x equal to x1, so this is your alpha 1, you substitute alpha 1 here, there is determinant here also, you have to find out determinant also. When they will cancel out, you will get this numerator and denominator will cancel out, you will get 1, and this term will be 0 and this term will be 0 for the first case. Similarly for the second and third. Okay, only n2 will be 1 when you substitute x equal to x2, y equal to y2, only n2 will be equal to 1 and rest all will be 0. So this is the property of shape function. What is the property of shape function? It sums up to 1. So if you have n1 plus n2 plus n3, it is always equal to 1. Okay, it is always equal to 1. That is the property of shape functions. We will see what are the properties of shape functions in the next class. So along with that, we'll solve a problem on 2D triangular element or 2D simplex element. Okay, thank you.